Welcome back everyone. In this video, we'll continue our journey into linear regression, starting with a quick recap of simple linear regression and then extending it to multiple linear regression. Let's start with a quick reminder. In simple linear regression, our goal is to predict a numeric outcome from one input variable. Here is a small data set. Each observation here has one input x to I and has one output y to I. Altogether, we collect m data points represented as column vectors x and y. On the right, you can see a scatter plot showing the relationship between the study hours and exam score. Here, each point represents one student, their study hours on the x-axis and their score on the y-axis. The idea is to model the relationship with a straight line. We then make predictions and measure how far off they are from the actual values using the mean squared error. The goal of training is to find the line that minimizes these errors, in other words, the best fitting line through the data. To minimize the cost function, in this case mean squared error, we use the gradient descent. The idea is this: we start with initial values for beta 0 and beta 1, and then we repeatedly update them to reduce the error. At each step, we calculate the gradient, which shows the direction of steepest increase of the cost function. But since we want to minimize the cost, we move in the opposite direction of the gradient. That's why the update rule looks like this. We use beta 0 minus the learning rate times the derivative of the cost function with respect to beta 0. To update beta 1, we use the following: beta 1 minus the learning rate times the derivative of the cost function with respect to beta 1. Here, alpha is the learning rate. It controls how big a step we take in that direction. If alpha is too large, we might overshoot the minimum. If it's too small, learning becomes very slow. This process continues until the updates get very small, meaning we've reached the point where the cost is minimized. After we calculate the partial derivatives, the update rule looks like this. Now that we understand how simple linear regression works, let's step back and ask, is one feature enough? Imagine two students who both study for 5 hours. One scores 95 and the other scores 60. Same amount of study time, but very different results. Clearly, something else must be influencing performance. Maybe their past exam scores, their sleep, or even stress levels. This is a limitation of simple linear regression. It only captures one relationship. To model the reality better, we need to include multiple factors that might affect the outcome. Now let's look at an example of multiple linear regression in action. Here, our goal is to predict a numeric outcome from two input variables. On the left, you can see a sample data set. Each observation here has two input features, x1 to I and x2 to I. These are individual data points. And y to I is the exam score, the output. For instance, this could represent something like predicting exam scores from study hours and past grades. We can represent all the data compactly in the matrix form x for all input features and y for the output values. On the right, we visualize these points in 3 dimensions. The horizontal axis represent our two input features, study hours and past exam score, and the vertical axis shows the target variable. The goal of multiple linear regression is to fit a plane, not a line, that best captures the relationship between these variables. The plane is defined by this: y equals beta 0 plus beta 1 x1 plus beta 2 x2. And it's positioned so that the total error between the plane and the data points is as small as possible. Using this plane, we make predictions, then measure how far those points are from the actual data points. That's our error measured using the mean squared error. Once we've defined our model and cost function, the next question is how do we find the best parameters? We again use the gradient descent. It's the same idea. We start with random values for beta 0, beta 1, and beta 2, and repeatedly update them in the opposite direction of the gradient of the cost function. Each parameter is updated simultaneously, and we keep repeating this process until convergence. And of course, the learning rate alpha determines how big each step is. After calculating the partial derivatives here, the update formula looks like this. If we look at the update formula carefully, here we see x1 to I and x2 to I. This means that we are adjusting each beta j based on how much that feature contributes to the overall prediction error. So why do we even need multiple linear regression? Because in real-world situations, outcomes rarely depend on just one factor. Using a single feature is a very limited view of the data, but adding more features gives us a richer and better predictions. When we do multiple linear regression, mathematically we are no longer fitting a line, we are fitting a hyperplane. So the more relevant information we include, the better our model reflects reality and the more accurate our predictions become. Now let's connect the map to data. Here is a sample data set with multiple features. Here each row represents one observation and each column is a feature like study hours or sleep. And here n is the number of features, m is the number of observations, and x1 to I, xn to I, they're individual data points, and y to I is individual outcome data point. And we can represent all these inputs compactly using matrix notation. Here the matrix X contains all our input features, while the vector beta holds the parameters we are trying to learn. This setup makes it much easier to work with larger data sets and compute everything efficiently. In fact, we can write down our model and cost and everything using the matrix notation, but I'm not gonna get into that in this video. Now, how do we train this multi-feature model? The process is almost identical, only now we are adjusting multiple betas at once. Our goal is to find the set of coefficients that minimize the cost function. Gradient descent works by nudging all parameters in the direction that reduces the error the most. We keep iterating until the cost flattens out, meaning our model has learned by best fitting hyperplane. And this is how the update rule looks like. Again, here in the sum, we multiply by the values xj to I. This ensures that parameters connected to more influential features get adjusted appropriately. In other words, gradient descent tunes every coefficient based on how much the feature contributes to the prediction error. Here is a practical issue, feature scaling. When features are on different scales like study hours 0 to 20 and pass scores 0 to 100, gradient descent can get confused. It moves unevenly across the cost surface and may take forever to converge. To fix that, we standardize each feature by subtracting its mean and dividing by its standard deviation. This brings everything to a similar range, typically -1 and 1. And once we scale our features, cost function becomes much smoother and gradient descent converts way faster. So before training any model, always check your feature scales. This simple step can save a lot of time and frustration. So when you should use multiple linear regression, it's perfect when your target variable is continuous, the relationships are roughly linear, and your features are not too correlated. It's a solid baseline model, simple, interpretable, and surprisingly powerful for many practical problems. In the next video, we'll talk about evaluation metrics, how to measure how well our model is doing, R-square and adjusted R-square. We'll also look at how to improve the model's performance. Thanks for watching. If you found this helpful, don't forget to like, share, and subscribe to the Mutlu Learning Hub for more data science and machine learning content. See you in the next one.